Hey everyone. In this mini lecture, the next method that we'll consider for solving particle kinetics problems is going to be obtained by integrating the equation of motion with respect to time. So the result is usually referred to as the principle of impulse and momentum. So we can apply it to problems involving both linear and angular motion. So this principle that we're going to use is very useful for solving problems that involve force, velocity, and time. And it can also be used to analyze the mechanics of impact that you'll study more along in the future. So here's our first example. We have a zero point 0.5 or 5/10 kilogram ball that strikes the rough ground and rebounds with the velocities shown. We neglect the ball's weight during the time it impacts the ground. So we're asked to find the magnitude of the impulse. Okay, so in doing so, we have to come up with a plan. So our plan is to first apply, apply the principle of impulse and momentum to determine the impulsive force. But we're also going to draw the momentum and impulse diagrams of the ball as it hits the surface. So here they are. All right, so in solving this problem, what we're going to do is use the impulse and momentum diagrams. And as shown, the impulse caused by the ball's weight and the normal force, so that impulse that's caused by the weight and the normal force that we see here, it can be neglected. So we'll do that because their magnitudes are very small as compared to the impulse from the ground. All right, so now the principle of impulse and momentum is stated as such. So we'll have the initial momentum of a system. All right, and we're going to take that initial momentum of a system and then we're going to add it to this piece here, which is known as the impulse. And then that's going to give us the final momentum of a system. All right, so then we're going to go ahead and plug in. So this yields for us 0 and 5/10 times 25 cosine 45 degrees, I minus 25 sine of the 45 degrees, the j direction. All right, so plus, and then we have from T1 to T2 F with respect to dt. All right, so then that's going to equal for us 0.5 times 10 cosine 30 degrees I plus 10 sine 30 degrees j. Okay, so in looking at it, the impulse vector, right, we'll call I, capital I, from T sub 1 to T2 with respect to T is going to be 4.509 I plus 11.34 J. Right. And then we can go ahead and get the magnitude. So this was for us the impulse vector. And now go ahead and get the magnitude. And for us, the magnitude is just going to be taking the square root of 4.509 squared plus 11.34 squared, and that gets us 12.2. Okay, so in our next example, what we have here, we're given the spring constant being K is equal to 10 kilonewtons per meter. M sub A is 15 kilograms. V sub A is 0 meters per second. M sub B is 10 kilograms, and V sub B is 15 meters per second. The blocks, they actually couple together at impact, and we're asked to find the maximum compression of the spring. So first we need to plan. So we consider both blocks as a single system and apply the conservation of linear momentum, which you should have read about. And we're going to use that to find the velocity after impact, but before the spring actually compresses. Then we're going to use the energy conservation, to find the compression of our spring. Okay, so let's go ahead and work through it. So we're going to use, as stated, the conservation of linear momentum. So positive to the right. So we have M sub I, V sub I sub O, and that's equal to M sub I, V sub I. All right. Next, we're going to get our values, which would be 10, negative 15I, and then that's equal to 15 plus 10. Alright, so then V is equal to negative 6 meters per second. And we can rewrite it as 6 meters per second and notate going in that direction to the left. Alright, and next we go to the energy conservation equation. Alright, so that's going to be T1 plus V1 equals T2 plus V2. Alright, so here we have 0.5 times, that should be 15, right? Yeah, 15 plus 10, negative 6 times 2 plus 0. Alright, and that's going to equal 0 plus 0.5 times the 10,000 times S sub max squared. Alright, so, and then taking all that into account, the maximum compression of the spring is S max, which we can go ahead and find to be 0.3 meters. In example 3, we're given 2 rail cars with masses of M sub A is 20 and M sub B is 15 and velocities shown. Let's find, or we're asked to find, the speed of the car A after collision if the cars collide and rebound such that B moves to the right with a speed of 2 meters per second. We're going to find the average impulsive force between the cars if the collision place in 0.5 seconds. All right, what's our plan? Our plan is to use conservation of linear momentum to find the velocity of the car A after the collision, and all internal impulses cancel. Then use the principle of impulse and momentum to find the impulsive force by looking at only one car. All right, let's take a look. Okay, so we're going to use that conservation of linear momentum, right? So we'll look in the x direction, right? M sub A, V sub A1 plus M sub B, V sub B1 equals M sub A, V sub A2 plus M sub B, V sub B2. All right, here we have the 20,000 times 3 plus 15,000 negative 1.5, and it's equal to 20,000 VA2 plus 15,000 times 2. So solving for V sub A2, doing that calculation, we should get 0.375. All right, and then looking at the impulse and momentum on car A, right? And this is in the x direction, car A. So we have M sub A, VA1, all right, F here with respect to T, MA, VA2. Okay, so then that gives us 20,000 times 3 minus F with respect to T equaling 20,000, 0.375. All right, so that integral of F with respect to T is equal to 52,500. All right, it's looking good. All right, and then we're going to look at the average force. All right, so the average force, so that F with respect to T is 52,500, and that's equal to F average times 0.5 seconds. Okay, so then F average comes out to be 105 kilonewtons.